it looks like. Let's go ahead and get started. I'm going to take myself off camera to save some bandwidth here. But we are back for part 2 of our 3-part HazCom series, and today we're going to be talking about the hazards of air emissions. So to recap what we discussed last week, this particular course is modeled on a training course that we do in industry because OSHA requires employers to tell employees that they have the right to know about the hazards of chemicals in the workplace. So we have this basic chemical hazard communication course to get employees up to speed. There's also a law that was passed within 6 years of the OSHA standard, the Emergency Planning Community Right to Know Act. And this EPA law and regulation says that community members have the right to know about hazardous substances in our communities. So with this, we are the Jefferson County Local Emergency Planning Committee, LEPC. We are authorized by that EPCA Act. And we're kind of bringing it all together. We feel that along with the right to know comes the responsibility to understand, and knowledge is power. So we want to bring this vocabulary, bring these insights to the community members who are interested and want to know. Okay, getting into our technical content now. We talked about different kinds of hazardous chemicals, and our overarching theme is that just because a chemical is hazardous doesn't mean it has to be dangerous. And if you recall, I said, if you know what the hazard of a chemical is, and you know how to manage that hazard, and you do effectively do the thing that manages the hazard, then you can mitigate the danger. The hazard is inherent to the chemical. That's a property of the chemical, but it doesn't have to be dangerous if you are effectively managing it. When we talk about hazardous chemicals broadly and generally, there are several different ways we can slice and dice it. We can talk about their physical hazards versus their health hazards. We can look at the 4 broad categories of chemical hazards being flammability, corrosivity, reactivity, and toxicity. And we can talk about the effects of these chemical hazards being acute, happening right here, right now, or chronic, manifesting over time. Specific to toxins, there are 4 possible pathways of exposure: inhalation, ingestion, absorption, and injection. Those last 2, absorption and injection, do require direct physical contact with the chemical. So those are much more of a concern in a workplace setting, occupational exposures. Inhalation and ingestion, though, do cross over to public health regulation. Of course, inhalation, we all want to breathe the same clean air. In ingestion, we don't want our water sources and our foodstuffs to be contaminated. Also, when we're talking about toxins, these are the things that have a toxic or poisonous effect. You need to have a source, a pathway, an exposure, and a toxic dose. If any one of those 3 is missing or interrupted, you can break this chain and you can avoid having a toxic effect. You may still have a source and a pathway, but if you don't have an exposure, then you don't have the toxic effect. Or if the exposure is below the toxic dose, you wouldn't have that effect. And we talked about the dose makes the poison. We talked about having to eat 588 pears to have a toxic dose of formaldehyde from the naturally occurring formaldehyde. On that note, we said just because a chemical is present does not mean it is harmful in the amount present. So the pears example, we talked about contaminants in Lake Erie. People go splashing around in that all the time, even though we know that it's not pristine, perfectly pure water. So the contaminants just aren't present. That's why you have to have a toxic dose. We did switch gears and we started talking about how you can recognize these chemicals when they're marked. We talked about OSHA's 2012 updates to their hazard communication standard to make it a globally harmonized system. So now we're using internationally recognized markings on our chemical containers. We showed you some of the pictograms that you'll see on specifically OSHA GHS labels. We talked about DOT, Department of Transportation labels and placards that you'll see on tractor trailers and rail cars and things like that. We started to look at some of these sources of additional information. The safety data sheet is often expected to do more than it really does. It is a document prepared by a chemical manufacturer for the workplace user. And a lot of times they shortcut and put not applicable or not determined because it's not really relevant to the workplace use of that chemical. But it is better now since the globally harmonized standard than before. We talked about the NIOSH Pocket Guide to Chemical Hazards, and that's a much more complete and reliable source of information about specific chemicals. The web link is there, but I also did email it out to everybody who attended last week's class. And then we talked about the Emergency Response Guidebook as being a super quick way to look up emergency response info. This is really the go-to resource when you have a unfolding emergency right here, right now. This is the quickest way to get good, reliable, appropriate, hands-on emergency response information. And again, I emailed that link to everybody. Last week, we introduced the concept of toxic inhalation hazards, and we will get into that in much more detail later today. So let's dig in. Okay, so we know that different chemicals have different hazards. That was the main point of last week's class. Different chemicals have different hazards. And so today we're going to point out that these chemicals are regulated differently because they have different hazards and where those hazards are present. So if we're talking about workplace exposures, that's going to be OSHA's jurisdiction. OSHA is all about making sure that workers are safe in the workplace, including their chemical exposures. If you have a hazardous material in transport on the roads, on the rails, on the river, that's going to be the U.S. Department of Transportation. It's going to regulate how hazardous materials need to be prepared, packaged, manifested, controlled, stabilized in transport. And then the U.S. EPA, along with state, tribal, and local partners, regulates these chemicals in our ambient communities. So air emissions, water quality, water discharges, waste management, hazardous substance inventories at facilities, and any releases to the environment. Now, I want to stress EPA and its partners. So US EPA essentially establishes federal standards and publishes them. US EPA does have an enforcement branch, but from a day-to-day reality, most enforcement, most permitting, most reporting happens at the state and local level. So here in Kentucky, we have the State Division of Waste Management, the State Division of Water. Locally, we have the Louisville Metro Air Pollution Control District and the Metropolitan Sewer District. So all these together in collaboration with each other regulate how these materials are handled, emitted, discharged in the environment. Okay, so now let's drill down a little more specifically and talk about air pollutants, because this is one that gets a lot of interest. So just as different chemicals are regulated differently, different air pollutants are regulated differently because they have different hazards. And also, it's important to understand that these air regulations have evolved over time. So we know a whole lot more about certain kinds of pollutants in 2026 than we knew in 1990 or 1970 or 1950. And as our understanding grew, the regulatory universe expanded to match what we knew. As we knew more, we did better. So I'm not going to go into this slide specifically in a lot of detail, but just showing that, what we started with in 1970, the Clean Air Act, and as we knew more, we started passing different regulations to become the regulatory landscape we have now. Okay, so here is our hypothetical facility, and this facility is going to be emitting all sorts of different pollutants. And I know there's a lot of acronyms there. The specifics aren't as important as the generalities, okay? And this is color coded, and we'll break this down on the next several slides. We're not going to talk about it on this one big oversight slide, but similar to the slide before, where I had it in chronological order, you see here the black and white pollutants are the criteria pollutants regulated by the 1970 Clean Air Act. And then the orange pollutants were added in 1987 as they were ozone depleting substances. By 1990, the Clean Air Act amendments started regulating hazardous air pollutants. By 2005, the district's STAR program, Strategic Toxic Air Reduction, started targeting the ones with the red cloud bubbles around them. And by 2020, the federal AIM Act started regulating some greenhouse gases. So we'll do each of these in turn. So criteria pollutants first. So these have been regulated for the past 56 and a half years, right? Going back to the 1990 Clean Air Act. So you have to kind of go back in time and appreciate what did we understand about air pollutants in 1970. And so we were looking at the big obvious things, the things that in 1970 they knew were a problem. So carbon monoxide, which is a combustion product, that was not known to be a problem. In 1970, lead was a big problem because in 1970, all the gasoline had lead. So when you combusted your gasoline engine in your car, you were emitting lead into the atmosphere. So lead was a big problem in 1970. Nitrogen dioxide, that's also a combustion product. Particulate matter. So these are particulates and some aerosols that have mass that can be filtered and collected and measured. They can also be problematic inside your lungs because they have mass. It's a foreign body. So that was a problem. Sulfur dioxide is an emission primarily from the combustion of fossil fuels and other sources, but it's problematic because when it reacts with water in the air, it becomes acid rain, a very dilute solution of sulfuric acid. And then ground level ozone is known to be a problem for the past many decades. Now, nobody's actually directly emitting ozone. There's no factory or engine or source out there that's pumping ozone into the air. Ozone is formed in the atmosphere when these ozone precursors made up. And I have another slide on that specifically. So hold that to the side. What I want to show you on this slide is that for all of these criteria pollutants, if you look at that table on the right, EPA established national ambient air quality standards. And they said, based on what we know about these pollutants and how we know them to affect human health and the environment, we're going to establish these national ambient air quality standards, these NAQs. And in the far right column, that is a concentration, like 9 parts per million carbon monoxide in an atmosphere, 35 parts per million. Or for lead, it's 15 hundredths of a microgram per meter cubed. Okay, so each of these is measured. And the thing to point out is that these are the levels that the air outside, that you go outside and breathe right now, should be below those standards. If it's above those standards, it's considered to be unhealthy. And so the basis of state and local permits that are issued to facilities are to keep the airshed pollutant levels below these levels. These levels are also revisited at a minimum every 5 years. They are reviewed. And if the science has evolved and a different level is now considered to be more appropriate, they will change it. If the level is reviewed and it seems to have held up, they will maintain that level. Okay, this is where we get the idea of the air quality index. This is something, if you see this in your social media feed, or, I've seen TV commercials, or, sometimes the newspaper or the radio will mention the air quality index, particularly the weather forecast. They might mention the air quality index. And this is taking whichever criteria pollutant is anticipated to be the most concern for that particular day. Now, here in Louisville-Jefferson County, the air quality index is almost always going to either reflect ozone or particulate matter. Okay. We're now 2026, 56 years removed from the Clean Air Act. Lead is not a primary concern. Sulfur dioxide is not our primary concern. We're talking about the ambient air outside. Carbon monoxide is not our primary concern. The ones that we're concerned about here are particulate matter or ozone. And this is going to be a number on a scale of 0 to something. And if you're, I want you to consider that number to be a percentage of the anticipated or modeled or measured value against the health-based threshold. So these NAAQS levels, right? These National Ambient Air Quality Standards. So, for example, you look at ozone. The ozone NAAQS there at the bottom right is 70 parts per billion. So if ozone is today's primary pollutant of concern, the air quality index is going to say, how close are we to meeting or exceeding 70 parts per billion? And if your number is AQI of 50, that means we're only predicted to hit 50% of 70 parts per billion. So we're anticipating levels in the ballpark of 35 parts per billion. If your number is 100, it means we're going to get 100% of 70 parts per billion. And if your air quality index goes to 105, it means we're going to exceed the 70 part per billion standard by approximately 5%. So, in the same thing, if you look at particulate matter, let's say PM 2.5, the standard is 9 micrograms per meter cubed. PM 2.5, that's very fine particle pollution. 2.5 microns or smaller in diameter. And if you have an AQI of 90, that would mean you'd be just under the 9 microgram per meter cube number. Okay, so that's what this is measuring. Most days throughout the year are either going to be green or yellow. The vast majority of days are going to be less than 100% of the air quality standard of concern. But there will be days, particularly in the summer months, when ozone is high, that you'll get air quality alerts because the air quality index is going over 100. So let's talk about ozone. This is a seasonal issue, right? We are actually in the ozone season. Different regulatory authorities have different start and end dates. So I know the slide says May 1st to September 30th. The local Louisville Metro Air Pollution Control District, I think they actually have moved their start date up to March 1st is when officially they're looking at it. They just had their monthly meeting this past week, and we have not had any air quality alert days so far, which is to be expected. So why is that? Why is ozone seasonal? So ozone, ground level ozone is formed when volatile organic compounds, VOCs, like paints, inks, solvents, coatings, fuels, like specific examples like xylene or benzene or toluene or ethylbenzene or anything like that. When those inks, coatings, solvents, fuels react with nitrogen oxides, which are a product of combustion, in the presence of direct sunlight. So you have to have enough VOCs in the atmosphere. You have to have enough nitrogen oxides, NOx, in the atmosphere. And there needs to be direct sunlight to cause them to react together. And that's what makes it a seasonal problem. Of course, during the winter, we still have VOC emissions. We still have nitrogen oxide emissions, but the northern hemisphere is tilted away from the sun, so we don't have enough direct sunlight to create enough ozone to trip the National Ambient Air Quality Standard. But in the summer, as we are tilted toward the sun, that third factor, which is the direct sunlight, works against us. And so this is why it's a seasonal problem. So ground level ozone is bad. This is the ground level ozone, in the troposphere, the air where we live, work, and breathe. And ground level ozone does cause respiratory issues, particularly for sensitive populations, the elderly, infants, small children, and also for individuals who work outside and are directly exposed to high ozone air all day long. So when you have an air quality alert for ozone, an air quality action day for ozone, it's because the conditions are right for the formation of excessive concentrations of ground level ozone. Not to be confused with stratospheric ozone. This is the ozone way, way up in the upper levels of the atmosphere, where stratospheric ozone is good for our planet. We want that ozone layer around the planet to be intact. But what we found out going back 40, 50 some odd years ago, in the 1970s and 1980s, scientists were starting to put together that certain chlorofluorocarbons, hydrochlorofluorocarbons, and other actors were acting as ozone depleting substances in the stratosphere, in the uppermost level of our atmosphere, and particularly over the poles, over the Arctic and the Antarctic. These CFCs and HCFCs would accumulate, and they would basically eat holes in the stratospheric ozone layer that allowed excess levels of ultraviolet radiation to penetrate the atmosphere. And if left unchecked, these increasing UV levels were going to cause a lot of skin cancer issues and other similar issues to those of us living on the ground. So by 1987, the United Nations took this issue up, and the scientists made their case and said, look, if we don't get these ozone depleting substances under control, we're going to have world health crisis here because of these increasing levels of ultraviolet radiation. Now, here's the great part of this story. This is a success story. All 100%, imagine this happening today, 100% of the member nation states of the United Nations and some other entities that weren't actually nation states, everybody signed on to the Montreal Protocol that says, yes, we acknowledge that this is a problem, and we will each do something within our own levels of jurisdiction to limit and reduce chlorofluorocarbon and hydrochlorofluorocarbon emissions. And so CFCs were pretty much eliminated in short order, and the HCFCs have been phased out over time. This is why, if any of you have had servicing or repair on an air conditioning system or a refrigeration system or something anytime recently, if you're paying attention, those contractors have to have certain qualifications, certain credentials, certain licenses. They have to collect the hydrochlorofluorocarbons like the Freon and the other refrigerants that were in that system. They have to collect it and containerize it and take it back for recycling. They can't just vent it to the atmosphere, whereas 40, 50 years ago, you just let it go to the atmosphere because nobody knew any better, right? So this is a success story because everybody has been reducing and limiting and phasing out these ozone depleting substances. The holes in the atmosphere, the stratospheric ozone layer, have been shrinking. And the last I heard is that the projected is by 2040, we should be back to pre-Montreal Protocol levels and then keep getting better. So this is a good news story. Not to be confused with greenhouse gases. The only thing they have in common is we're talking about way up in the stratosphere, right? It's where this occurs, but these are completely different pollutants. Now, some ozone depleting substances are also greenhouse gases, but not every greenhouse gas is an ozone depleting substance, okay? With greenhouse gases, we're looking at an accumulation of these materials in this upper level of the atmosphere. And what's happening here is solar radiation, normally a healthy atmosphere, a healthy planet, solar radiation comes in, and a good portion of it bounces off the Earth. Specifically, it bounces off the reflective properties of the oceans and the other waters, right? So it bounces off and it radiates back out into space. So this radiation that causes warmth comes into the planet atmosphere, bounces off the ocean, goes back off in outer space. And for millennia, many millennia, the planet has had a sort of equilibrium. But in recent history, since the Industrial Revolution, we've been emitting greenhouse gases steadily over the past couple hundred years, that we've created an overaccumulation of these greenhouse gases in the upper level of the atmosphere. And essentially, it's inhibiting the bounce out of the reflective heat radiation. So it ends up being trapped inside the atmosphere as if we had a wet blanket up top. Now, not every greenhouse gas is equal, right? So we all talk about carbon dioxide, CO2. That's the reference value. All the other greenhouse gases are compared to carbon dioxide. So we give it a unitless number of 1. And if your other greenhouse gas has a value smaller than 1, it means it's not as effective at trapping greenhouse gases as carbon dioxide is. If your number is bigger than 1, it's more effective at trapping this heat. So water vapor, like clouds, yes, clouds can be a greenhouse gas, but it's only 1,000th of the global warming potential that carbon dioxide has. So it has a very small GWP value. Methane, so you heard about farting cows, right? Methane is the gas, the compound, CH4, that cows would fart. And cow flatulence, let's be classy here, right? Methane has a global warming potential of 28. So on a pound by pound basis, a pound of methane has 28 times the global warming potential of a pound of carbon dioxide. Okay, so that sounds significant. Nitrous oxide, this is the laughing gas that, not so much anymore, but sometimes dental procedures will still use nitrous oxide as an anesthesia. Nitrous oxide has a 265 times the global warming potential of carbon dioxide. Then you get into some HCFCs and CFCs. Now, those are coincidentally, the same things that were over here. They were considered ozone depleting substances. Well, they're also greenhouse gases as well. HCFC 22, that is Freon 22, the Freon 22 from your refrigerator for your air conditioning system, your old fashioned refrigerator air conditioning system. It's got a global warming potential of 1,760 times carbon dioxide. CFC 12, which is largely phased out by now for its ozone depleting reasons, not for this, but CFC 12 would have a global warming potential of 10,200 times carbon dioxide. And then HFC 23, which is not an ozone depleting substance. Hydrofluorocarbon 23 has 12,400 times the global warming potential of carbon dioxide. So for every pound or every ton of HFC 23 emitted, it's over 12,000 times more potent as a greenhouse gas as a pound or ton of carbon dioxide. So as recently as 2020, the Federal AIM Act actually passed limits on the amount of HFC 23 that can be emitted. Okay, hazardous air pollutants. Now, this is something entirely and completely and totally different. So if we look at our fictional plant here with these different kinds of pollutants, they said that xylene is a type of volatile organic compound, right? It's an example of a solvent. But if we take this and swing it over to the other side, now we're looking at specific chemical compounds like xylene, like chlorine, Cl2, like hydrogen fluoride, HF, like hydrogen chloride, HCl. These specific chemical compounds are known to have toxic or hazardous effects above a certain dose or concentration in the atmosphere. So when Congress passed the 1990 Clean Air Act amendments, that's 36 years ago now, right? They had national emission standards for hazardous air pollutants called NESHAPs. And these NESHAPs had specific regulations to require maximum achievable control technology, MACT, to limit and regulate the emissions of these specific hazardous air pollutants, HAPs, because now we knew better. Okay, it's not just a broad category of emissions, it's this specific chemical, xylene, this specific chemical, chlorine. So we have MACT standards for those. At the local level, in 2005, so 15 years after the Clean Air Act amendments, Jefferson County created its Strategic Toxic Air Reduction Program, the STAR program. And it's also using a risk-based approach to model and measure the ground level concentrations of these specific, under the Clean Air Act, they would have been called hazardous air pollutants. Under the STAR program, they're called toxic air contaminants, TACs, whatever you call them, they're the same chemical, right? So the STAR program has standards in place to limit the amount that can exist at ground level and expose neighbors. So this is all about a risk-based approach to minimize potential lifetime exposures, particularly in environmental justice neighborhoods where individuals maybe have a higher exposure than somewhere else. We want even the person with the highest exposure to have an acceptable exposure below that toxic dose. Okay, then we can look at some of these same chemicals, not all of them, but of the examples I have on the slide here. If a facility has a certain quantity of hydrogen fluoride in storage or a certain quantity of chlorine in storage, they are required to have additional layers of protection, additional procedures and protocols in place to minimize the likelihood of a release. And it's all volume based, because the theory is if you have more, you're more likely to have an accident. And so they look at the sources that maintain the highest inventories, and they require these additional protections built into the program. Okay, so now let's talk about what happens if you have an accidental release. Okay, so we got a little more understanding under our belt. We've got last week's vocabulary, and now we've got this basic understanding of different kinds of air emissions. But an accident, nobody's planning to have an accident. So when a chemical is released, wherever it is released, however it is released, the first thing we need to ask is, what was released? What is the chemical? What are the hazards of that chemical? Is it a flammable chemical or a corrosive chemical or a reactive chemical or a toxic chemical? Or maybe it's not even classified as a hazardous chemical because it doesn't meet the criteria, the regulatory criteria, to be classified as flammable or corrosive or reactive or toxic. Okay. Remember, toxic means poison or poisonous, but not every chemical is toxic or poisonous, just the ones that are anticipated to cause health-based issues at the anticipated concentrations. So, as an example, if we have a release of a flammable chemical somewhere, a rail car or a facility or whatever, a tank, a flammable chemical is the biggest hazard is that it could catch fire. So the people who are right there near to it, basically the responders, the facility people, the railroad people, wherever it is, those are the ones most endangered. It's most hazardous, anybody who's going to be close to a potential fire. Now, if it does catch fire, now just because the flammable is released doesn't mean you're going to have a fire. You also have to have an ignition source. So ideally, okay, so let's say the flammable material is released, you have a great big puddle of gasoline on the ground. Well, then we don't want to introduce an ignition source. It's much easier to clean it up from a puddle state than a burning state. But if your flammable does catch fire, then we also have to consider the hazards of the fire and smoke and soot and other combustion byproducts. Now, if your chemical release was a corrosive, again, these require direct physical contact to be injured by the corrosive. Now, a corrosive liquid or corrosive gas. A corrosive gas is a toxic inhalation hazard. Still not up to that yet. We will talk about that in this slide deck, but set that aside. If you release a corrosive liquid, okay, a puddle of sulfuric acid, a puddle of sodium hydroxide caustic, again, it's going to be those responders in the immediate vicinity who are most at risk. You know, the neighbor quarter mile, half a mile away, they're not in contact with it. They're minimal, negligible risk. And then if what is released is a reactive material, well, then you have to ask, well, what is it reacting with and what are the byproducts of that reaction? A reaction that yields a toxic gas is going to be much more of a concern than a reaction that yields a flammable gas, because you have to treat what is it going to become. So let's talk about these chemical reactions. First off, universal truth. A chemical reaction will continue to occur until one of the reactants is fully consumed. And similar to that, a chemical reaction will cease to occur whenever either one of its reactants is fully consumed. So this is best explained with an example. So we're going to use the calcium carbide and water example that we showed you in last week's class. So when calcium carbide reacts with water, it's an exothermic reaction that will release heat, and it will yield acetylene gas, which is a flammable gas, and calcium hydroxide, which is a high pH material. Okay? That means that as long as you have unreacted calcium carbide and also unreacted water in contact with each other, this reaction will continue to occur. Period. You can't stop the reaction as long as both are present. But this reaction will cease to occur when either all the calcium carbide is used up or all the water is used up. So if you have a great big puddle with a few rocks of calcium carbide dropped in it, when those rocks of calcium carbide are fully reacted, we call that slaked out, then the reaction will cease because there's no more calcium carbide to feed the reaction. It will end itself. Or if you have a great big bin of calcium carbide, let's say a shipping container, right? 2.5 ton bin of carbide with 2.5 tons of calcium carbide in it. And a little bit of water breaches that container and gets inside. You'll have this reaction, but when that little bit of water is fully reacted away, it will stop. And so you'll have most of the box of calcium carbide is unaffected, and some of that material will have slaked out to become the calcium hydroxide. But as long as the two reactants are both present and in contact, the reaction cannot be interrupted. You can mitigate the hazard, but you can't stop the actual reaction. Okay, so what does happen when chemicals react? When I was putting the slide together, it was far too easy to get these cartoon images. Boom, right? Because this is what, cartoons and movies and everybody would have you believe. But that's not necessarily the case for every reaction. It's a cartoonish interpretation. Okay. In reality, the results of a chemical reaction will be specific to the reaction. So you have to know what these chemicals are going to do. As a reminder, when you have a reactive chemical, it's either going to create a hazardous condition or a hazardous chemical. A hazardous chemical would be a new chemical created, or it could create a hazardous condition, which may include detonation or overpressurization. So in this example, where aluminum reacts with water to yield aluminum oxide and hydrogen gas, that flammable hydrogen gas is only hazardous in one of two ways. Number one, if the flammable hydrogen gas reaches an ignition source, then it would absolutely catch fire. Or B, if it is tightly containerized inside a drum, inside a bin, inside a rail car, okay? And it has nowhere to go because gases take up more volume than solids and liquids. So it can create an overpressurization situation. So those are the two ways it can be hazardous: if it reaches an ignition source or if it overpressurizes its container. Okay, so is overpressurization a fancy way of saying explosion? And I'm not going to subject us to the 23-second video, but you can imagine, okay, this woman up here in the video, she blows and blows and blows and blows and blows and blows into that balloon, and the elasticity of the balloon is finite. 23 seconds later, pop, the balloon pops. So the question is, did the balloon explode? And the answer is no. The balloon didn't explode, it overpressurized. So, hazardous materials, vessels, and containers are designed intentionally to yield and fail in a controlled manner. So, these three images here, the one on the far left and the one on the far right, are both real world examples of a drum and a flow bin that both had some sort of reaction inside of them. And you see they got bulged out and overpressurized. The drum on the left maintained its integrity. It was sufficient to contain that overpressurization. The flow bin on the right, if you look at that hatch at the top, it overpressurized to a point where it couldn't take any more. And then it had a pressure relief hatch at the top that failed in a controlled manner to relieve the pressure. The two photos in the middle are simply of drum testing to show that in order for a container to be improved for hazmat shipment, a sample of that container is subject to these rigorous overpressurization tests to demonstrate that the containers will in fact yield and fail in a controlled manner. By contrast, an explosion, by definition, involves the release of heat. So I've given you two definitions here at the bottom. I'm not going to read them in detail. The one on the left is the OSHA globally harmonized standard definition of explosion, and it includes gas produced at a temperature and pressure to cause damage. The one on the right is the Department of Transportation definition of an explosion, and it's an extremely rapid release of heat. So an explosion is going to include this kind of fireball situation with the release of heat, where an overpressurization can simply be an overpressurization. So I know we're running close on time. I want to speed through these, but these two photos are actually the same facility. November 2024, when the Givaudan plant over on Payne Street had its incident, the same facility 21 years earlier was operated by D.D. Williamson, had a similar incident. What we know about this facility was that it's a food additives manufacturer. Okay, they produce caramel coloring for food. One thing you can anticipate is that food manufacturing facilities, by the inherent virtue of their nature of their operations, they're not going to have a whole lot of toxic and hazardous materials on site if they don't have to, because they're making foodstuffs, right? In both cases, they were heated vessels. In both cases, what actually did happen was the vessel just simply overpressurized and failed. Now, it failed catastrophically, yes. It was absolutely tragic all day long, yes. But in both cases, they were overpressurizations. It wasn't an explosion with a fireball. It was blunt force trauma that hit workers who were too close to the equipment, and they were just killed on impact, okay? So no less tragic, but it was an overpressurization. 2011, Carbide Industries, one of the rubber town companies, had an incident. Now, both of these excerpts are taken directly from the Chemical Safety Bureau report. And basically, this was not a calcium carbide reaction, okay, which would have been a chemical hazmat incident. The CSB report says it resulted when water leaked in the furnace, causing an overpressure event because the furnace had electrodes operating at 10,000 degrees. And when the water reached the 10,000 degree electrodes, the water suddenly became 10,000 degrees, which is a heck of a lot of steam that's going to immediately overpressurize and blow the whole thing apart. Now, in this case, quote, the furnace spewed powder debris and hot gases because it was a furnace. That was what was inside the furnace. So it's going to release whatever was inside, not because it was a reaction of an explosion. This was also a tragic, catastrophic overpressurization event with 2 fatalities. Again, workers who were too close to the unit when it occurred. UPS 2976 just last November. So this UPS jet plane, fully loaded with somewhere between 36 and 38,000 gallons of jet fuel to get it to Honolulu, crashed into the ground on top of a petroleum recycling facility with anywhere from 150 to 200,000 gallons of oil at the facility. So in this kind of event, was it an explosion? Yes. Okay. The jet fuel exploded when the plane hit the ground and the engine was already on fire. So that was an explosion. The acute hazards were, of course, the impact, the explosion, the fireball, and even the smoke would have been an acute hazard. The chronic hazards of this incident, and again, 15 lives were lost, 3 on the plane, 12 on the ground. Tragic loss of life, tragic catastrophe for our community. But the chronic hazards were all that hundreds of thousands of gallons of oil on the ground that didn't stay in those tanks because a plane landed on top of them. And so MSD was working for weeks and months afterward to reclaim, capture, and recover the oil contaminated, basically fire water. So, okay. So whether it's an overpressurization event or an actual explosion, the results are going to be very localized to where it occurs. The closer you are, the more likely you are to be at risk. This Courier Journal excerpt here is from February of 24, front page of the paper. This is a Sunday edition, says, if there's an explosion, we're going to die. And that is a direct quote from a resident who lives near to Rubbertown. And my concern with this kind of reporting is that I have no doubt that this person said that. No doubt that this person believes that. But believing it and saying it doesn't make it true, because there are 10 facilities in Rubbertown. Over the 80 some years that Rubbertown has existed, there have been explosions. And the neighboring residents haven't been killed by these incidents. It's always been the workers in the workplace. The same thing with the Givaudan overpressurization incident over on Payne Street. It's the people who are standing a few feet from the vessel that overpressurized that were killed. Now, I will admit, it's absolutely scary when pieces of the tank flew and landed in people's yards. But nobody did get struck because the odds of getting struck decreased significantly with distance from the source. Okay. The thing to remember when there is an incident is what chemicals are involved, what are the hazards of the chemicals, and where do they pose that hazard? Where's the hazard most likely to be? Okay, so what if it's a toxic hazard? Okay, this is the one that everybody wants to know about in this room. I'm bringing it all together, and I'm going to hand it off to my counterpart who's going to finish this session. So I'm not going to read through this slide, but I do want to introduce you to these characters at the bottom. Okay, so Noel and Lowell. And in between Noel and Lowell, there's a boundary, right? Lowell, L-O-A-E-L, this guy Lowell, he is receiving an exposure that is just above the observable adverse effect level. Okay, he's not dying, he's not critically injured, but he is receiving an exposure where he can manifest an observable adverse effect. Maybe he's got a headache. Maybe he's feeling kind of queasy. He's feeling an effect from his exposure. Noel is beyond that point. The exposure that Noel is receiving is beyond the observable adverse effect level. He's having an exposure, but his exposure is of this particular toxin is such that it has no observable adverse effect. Okay, so we measure these effects, the toxic effects for each chemical specific to what we know about the chemical. So we have these acute exposure guidelines and these emergency planning guidelines. I'll show you these in the next slide, for example. So an acute exposure guideline level, 1, 2, 3, or 4. An AEGL3, not 4, 1, 2, 3. An AEGL3 exposure on this table, the far right-hand column, is the highest level of exposure. So if you're exposed to hydrogen chloride, it's chemical specific, at a concentration of 620 parts per million over a 10-minute period, you could have a fatal effect. Or 26 parts per million over 8 hours sustained could have a fatal effect. An AEGL2 level is not quite enough to kill you, but is enough to really mess you up. Okay, that's those column in the middle, 100 parts per million for 10 minutes or 11 parts per million for 8 hours. And the AEGL1 level, you'll see those are all the same number. That's the lowest observable effect level. Anybody who's exposed to 1.8 parts per million hydrogen chloride for any amount of time is going to have an effect. So what does this look like? So on the far right, you've got your source. The person closest to the source could be receiving an AEGL3 exposure. He could die. The person slightly further away from the source is receiving a lesser concentration. They are, debilitated. They cannot self-rescue. They may have permanent injuries, but they can survive it. Then you got Lowell out here a little bit further, who's got an effect, but when the source is removed or when he is removed, he will recover fully. And then Noel is way out here beyond that line of demarcation where his concentration is not enough to cause an effect at all. Similarly, the ERPGs are for responders, okay, healthy, able-bodied individuals. It's worth noting that the AEGLs do presume to be protective for the old, sick, very young people with underlying health conditions. The ERPGs are specific to responders. Okay, so when a toxic inhalation hazard is released, this is where it all comes together. This is the one everybody wants to know about. If we had the kind of release of the kind of chemical that poses a toxic inhalation hazard, we're going to model the amount of release and where it's going to go. A simple model, and this is a one-step rmp.comp app that is online. It presumes all the worst case scenario parameters, and it gives you a toxic endpoint. In this case, we're modeling chlorine. And if you model a loss of 2,000 pounds of chlorine over 10 minutes, it says that the toxic endpoint is 1.3 miles from the source, presuming all the worst case scenarios. That's the difference between Noel and Lowell. Noel is beyond 1.3 miles. He's not got an observable adverse effect. Lowell is just inside that perimeter, and then everybody who's closer to it is going to have a greater effect, okay? So we can also do more advanced modeling, and this one here is the Aloha modeling. It's part of the Cameo suite. It's free for download from the EPA app. The download is the free part. The training is a little bit more. But what I did was I modeled a 2,000-pound release of chlorine from a source. Now, I did that because chlorine is typically shipped in 1-ton containers, 2,000 pounds, 1 ton of chlorine. It's approximately the size of a large adult hippopotamus minus the legs. So if you imagine a hippopotamus full of chlorine, that's 2,000 pounds of chlorine. If that 2,000-pound container were breached, what would it look like? And you put your parameters in, and you see the AEGL tables here, and it models it over here based on wind direction, okay? You can take the output of this model, the plume dispersion, and you can superimpose it onto a location. And this location is a community in far western Kentucky. And at the address where that pink cross is a chemical distribution warehouse that I know for a fact has 1-ton cylinders of chlorine. So if a 1-ton cylinder of chlorine were breached at this location under the meteorological conditions of the day that I ran the model, this is how that would be imposed on the community map. The individuals in these zones, anybody in that red zone would be receiving an AEGL3 exposure greater than 20 parts per million chlorine, and they would be potentially killed by this exposure. The guy in the orange zone is getting an exposure 2 to 20 parts per million. He's debilitated. He cannot self-rescue. He's going to have some serious injury from this effect. Up there at the top, you see Lowell with his exposure anywhere between 0.5 part per million to 2 parts per million. He's feeling an effect, but it's a temporary one. And then Noel over there off to the side, because he's not in the plume of the downwind direction, his actual current exposure is less than 0.5 parts per million. He's got no effect right now. But what if the winds shift, right? We can also protect ourselves against this. I'm getting ready to turn this over to Sarah. Sarah, are you there?
I'm here.
Okay, so I'm going to turn over here, show everybody that, if we have the scenario that we modeled on the left and we put it onto the right, the person who could be killed in that AEGL3 exposure, if we got them sheltered in place, and Sarah's going to talk about sheltered in place, their exposure may be reduced to an AEGL2 exposure. It's survivable. He's still going to have an effect, but surviving is better than dying. The person in the orange zone who had an AEGL2 exposure, if we'd gotten them into a safe shelter, maybe it could be reduced to a lowest observable effect. So they could have a transient effect as opposed to being debilitated. And then guy up here, Lowell, who was receiving a lowest observable effect, if he had been effectively sheltered in place, he might have no observable adverse effects. So the point of shelter in place is to reduce your exposure to a less serious exposure. And with that, I'm going to turn it over to Sarah. Sarah, I'll drive the slide deck for you. How's that?
Sounds great to me. Hi, y'all. So Corinne started us off with the shelter in place and how, obviously we all want to live to our fullest and that's going to help us do that. So now we're going to talk about how that actually works. So how to effectively shelter in place. First and foremost, you want to get inside quickly. That includes all of your pets, anybody in your family, your immediate area that's with you. You want to close all your windows, your doors, fireplace dampeners. Most importantly, you want to turn off those air intakes. So in the summertime, got that air conditioning rolling, you're going to turn that off. So are you going to be uncomfortable? Yes, but you're going to have a higher likelihood of surviving this event without any issues. In the wintertime, you want to turn off that heat. You can also put, if you live in an old house, a lot of us do in Louisville, you know that you have gaps under your doors and your window frames and things like that we all live with. So you want to make sure that you put a little dampened towel underneath those to kind of help close off any of that air that might come in. And then you want to stay inside until the all clear is given, because as the situation is still ongoing, you stay inside, you're going to have less likely of having those effects. And then, of course, there are the things not to do. We talk a lot about what to do, but not doing things is just as important sometimes. Don't go in your basement. You can see here that going in the basement, the fumes might be heavier than the air, and that's going to cause a problem if you're lower in the house. You don't want to call 911 unless you are actually having an active crisis in your home. Trust that schools know what they're doing. All schools, government buildings, etc., we all have a plan for how to handle these situations. So trust that they have that plan and that they know what they're doing. And once the all clear is given, go get those kids, whether they be at U of L or any of JCPS, the parochial schools, etc. Don't try to outrun it in your vehicle. And most importantly, out of all of these things, don't panic. Panicking makes everything worse. Plan ahead. In school, we always talked about what to do when there's a fire and you have a fire drill, and at home, you have a plan for how you're going to get out. This is the same thing. You want to make sure that you have a plan in place because muscle memory will take over. And practice may not make perfect, but it definitely is going to make it so that you know what you're doing. So you want to practice those exit drills, or Edith, as you see here. Have some supplies on hand. Have your food and water, some towels, anything that you see on here, and plus some things that you think you might need a little bit extra of. You want to make sure that you can keep track of what's going on so that when that all clear is given, or if the shelter in place is extended, like we had during the UPS event, you know what's going on. And finally, we have our Lens Alert and Smart 911. I talk about this a lot with my job with Metro 311. Lens alerts are those little things that come up on text, or maybe you get a phone call or you see it via email. You can sign up for lots of different ways to get contacted because it's the Louisville Emergency Notification System. You can get everything from the shelter in place like we had with the UPS event, or if there's a major road closure. 71 apparently was closed for hours today. You get that notification on those lens alerts. If there's a tornado coming through, you can also get things like that. You get to choose what kind of notifications you want, how often you want them, and how they want you to contact them. I have mine by text. Fantastic resource to have. I know what's going on all of the time. And on the other side of that is that Smart 911. It's a safety profile that you can have. When you used to call 911 from a landline, they knew where you were because it's a landline. Well, we all have cell phones. You could be anywhere. And that data is not, that location data isn't always super accurate. It could be 900 feet from where you're at. So having this safety profile through Smart 911, you can put on there if you have anyone in your home that has medications that they need to keep track of. My mom was on oxygen, so that was really important to have. If we had a fire, they needed to take that into consideration. But on the other side, you can also talk about who lives in your household, how many dogs you have, how many cats you have. If you come in, my dog is going to be behind a dog fence and a gate, and it might jump at you, but it's not going to bite at you. All that kind of information can be kept in there. So you can see on here at the bottom how to opt in with your cell phone, where you can text that. You can also go to louisvilleky.gov, and at the very bottom of our screen on the web page, you'll see how to go on there and sign up for those. Very, very important to have, and excellent resources to keep in your back pocket for lots of things happening in the city. And finally, our quick review for this part 2, hazards of air emissions. You can see on here, different chemicals are regulated differently. Not every air pollutant is regulated the same way, as they are regulated for different hazards. It's important to understand the hazards and what was released. Your toxic chemical exposures are compared to those reference guidelines that we talked about. Our buddies Knoll and Lowell, the AEGLs. And in the event of that accidental release of the toxic inhalation hazard, the plume dispersion, we talked about with that model and how that can be affecting your likelihood of survival, and how shelter in place will help all of those things go a little bit better. And don't forget about your lens alerts.
Awesome. And we actually came in under time compared to last week. We were an hour and 5 minutes. This week we're an hour and 4 minutes. So I am grateful to everybody who stayed all the way to the end. Next week we will have plenty of time. Our program doesn't even run a full half an hour next week. So bring all your questions. And we'll see you next week. Same bat time, same bat channel, 12 noon on Friday. Thank you all.
Thanks, everyone.